Me a little favor and grab. This is a few slides I sketched here with my nice handwriting about lighting. So this is your, oops, minimize that one. Here you go. So if you do me a favor, guys, go to chapter number 1. Chapter number 1 talks about the science of light. FYI, science of light. So I drew this beautifully in page 3. It's actually drawn in page 3, much better than I did. I drew for you guys the science of light. Light comes to us between the visible spectrum and the non-visible spectrum. You just remember, in order for you to see things, we have to generate light in that spectrum. That's called, you can see it here, between the violet all the way to the red. This spectrum is called visible. If I generate in this spectrum, I can see and make others see, right? If you generate ultraviolet or infrared, good luck seeing it. Can I have thumbs up, Chad? So to generate that picture, have to operate within the range of visible spectrum. Otherwise, the science of lighting is not going to work. You're not going to be seen. Okay, so that's the rectilinear book. So you guys are familiar with the visible spectrums: violet, blue, green, yellow, orange, red, right? There is infrared and there is ultraviolet. They go by the wavelength. The wavelength of the light, or the wavelength of the light, and the wavelength of a light. If the light is a sinusoidal wave right here, here's the wavelength. So from here to here, that's my wave. Here's one wave. Here's my wavelength of that particular light. This is the length. So the wavelength. So you can see, guys, so we have 750, longer wavelength, shorter wavelength. So when you have infrared, you have a long wavelength, right? You can see the wavelength is longer, or a shorter wavelength. Ultraviolet is a shorter wavelength. Cool, longer wavelength, shorter wavelength. And red has longer wavelength than violet here. Visible spectrum, who cares? Then, so this is the length. The second thing is wavelength here, guys. If we take the wavelength, divide it 1 by the wavelength, give you the frequency. The frequency of the light, who cares? Just science. If you get the wavelength divided by the frequency, but 1 divided by the wavelength will get you the frequency of that particular color, right? So let's start with red 750 meter. These are in meters, guys. You divide it by 1 divided by 750, that will get you a 0.0013. You divide it, that will give you 1.3 millihertz. 1.3 millihertz. I'm sure these are in nano, the wavelength in nanometer. There's a nano. Everybody knows what nano is? Meter, nanometer. Nano is 10 to the power minus 9. That's a nano. Nano, they call it nanometer. Nano is 10 to the power minus 9. See how short that little thing is? So this calculation is slightly different because you have to divide. So divide, also multiply by 10 to the power minus 9. You flip it to the other side. When you flip this one to the other side, oh dear, then it becomes 0.0013 times 10 to the power 9, right? And this will be 1, 2, 3, 1, let's say 1, 2, 3. So 1.3 times 10 to the power 6 hertz. Okay, so this is this becomes 1.3 million hertz. Who cares? So that's how they measure them in nanometer, the length, and in hertz. Here's one thing you have to understand. The higher the hertz, the more energy in the frequency. The higher the hertz, the more energy. So the ones that have short wavelength have high energy. Ultraviolet have high energy, right? What they use, guys, they use ultraviolet to kill bacteria because they have energy. Like in wastewater treatment plants, if you ever work there, they have light after they process the sewer system and separate the solid from the water. They want to kill the bacteria, so they have light, literally light, and the light is shining right on the water. And that light have ultraviolet waves so powerful that they can cook these bacteria and kill them before they dump them into the lakes. So there is application for ultraviolet, high energy, high frequency. Infrared, they use it, guys, your remote control, right? Work, sign of light. sight of light. You have to see it, so it works as control, infrared. And they also use it for vision, special vision for infrared. What we care about is this spectrum. Can I have everybody understand the spectrum from violet all the way to red? That's where we need to generate. Thumbs up, Chad. The frequency, the length, divide the length by 1 divided by the wave, give you the frequency of that length. The second thing I'm going to talk, so this is basically the science of light, the science of light. Comment, questions, any comments, any questions? The beginning. Why do we care? Because when you design a fixture like that one above your head, you need to make sure that you hit that visible spectrum. Otherwise, it's worthless. You can't see from it. Color mixing. If you guys go, I didn't draw it. If you guys go, please, to page 4, they have radiated and reflected, and you can mix colors together. And I'm not claim to be a scientist in mixing colors. So if you look at the first one, radiated. If you take a green, blue, it's not black, guys. Can you change the first one? It should be green, red, and blue. If you take a green, red, and blue, mix them together, all of them, the 3 of them together give you white. The green and the blue give you cyan. The green and the red give you yellow. And magenta is blue and red. Read this on your own, mixing colors to get the third color. Reflected, the same thing. If you take yellow, magenta, and cyan, and you mix these together, it's like a reverse function, almost a reverse function. You can get green, black from all of them, blue, and red. So either you take the fundamental colors and make them to get other colors, or reverse function them. Okay, so that's, we don't get guys engaged into designing colors and so forth. Just be aware that mixing colors, mixing 1 or 2 colors will give you a third color in lights as well as in anything, as well as in paint. Cool. Can I have thumbs up about this one? Okay, so that's what I'm going to emphasize, the color mixing. The second thing, guys, is a stroboscope effect. I have that word, stroboscope effect. That term they used in the machines. Imagine that each one of you guys is a rotating machine, and you are powered by a 60 hertz fixture, right? 60 hertz fixture, running 60 hertz, one circuit. What happened, guys, is because the frequency of the machine is 60, that rotate at 60, the frequency of the light is 60, right? At a certain time, the saw that rotating, because they're running at the same frequency, might look to your bare eye as not moving. What's wrong about that? If the saw is running and you're looking at it and you can't see it's running, is that danger or not? Danger. So the Smarter Than Chad decided, Jeff, my friend, if you have a factory, what they do, guys, to solve this problem, what they do is they run multiple circuits. So they will bring phase A, phase B, phase C. So when you have 3 phases, it will not reach the 0 point at the same time. So the 3 phases, the effect of the 3 phases, frequency of the 3 phases together, will, long story short, get rid of the stroboscopic effect, which is basically it allows you to see things rotate. Okay, so be aware. So what's in it for you? When you do a factory, just be aware that bring at least 2 circuits from 2 phases, not 1 circuit. Cool? And there's a lot of changes for you, but make sure that you feed the manufacturing floor, anything that rotates. Make sure you give it at least 2 circuits, so things does not look still to the bare eye. Okay, so that's your stroboscopic effect. Light intensity. If you guys, now this is where I want you, if you guys are sleeping, I want you to wake up. We'll talk about this one. When we talked about lights, guys, incandescent lights, the worst light that you can do, they actually generate in this range, the visible range. If you go to the fluorescent light, they generate light in the ultraviolet. So how can we see from this? The Smarter Than Chad decided that they could put some phosphorus. These bulbs that you can see, they paint them with phosphorus, and this phosphorus material convert the invisible light into visible light. Cool. So just be aware that a lot of fixtures generate light at the UV, ultraviolet, but they convert it through treatment, chemical treatment, inside the bulb, it will convert that light into visible light. Okay, so that's the science of light. I hate to get into the science and remind you of a science teacher. This is in it for you guys what to understand. Now, who cares? Aaron, my friend, let me tell you one other thing. When you guys graduate from here, you can be a licensed, certified lighting designer. You can make more money as becoming certified lighting designer, a certificate that you can get. So if you are working in high-profile lighting jobs like theaters, government buildings, hospitals that need a lot of calculation, a lot of visual things, they require you to be a certified lighting designer to work on these projects. For two reasons. Number one, because you are smart, you know how to make things look good inside the building using light. And number two, you also know which efficient light to use in certain locations. So be aware, if you're to become a certified lighting designer, this material you have to review. They test you, IES of North America, and they have tests that certify people to be licensed, certified lighting designer. Okay, now moving into, so we moved away from the science, guys. We talked about generating an invisible spectrum. The second part I would like you to look at is light intensity. And this is, believe it or not, light intensity. Light intensity is measured in foot candle. That's what visual was doing for you guys. So with this, I'm going to flip to show you where, when we did visual, right in here. Do you guys see that one? This stuff that we did right here, all these dots, the 61, look at these, my dots, 61 and 54, and all this calculation. This is called light intensity. Foot candle, cool? Thanks God to the software. It calculates it for us. Now, what happened if you want to find that foot? Can you guys see that foot candle right in here? What happened if I want to do a calculation from that foot candle that says 58 here from all these fixtures? Can you guys see these fixtures? So there will be contribution from this fixture right in here, and I will do the calculation right at this point. Do you guys agree with me? There will be contribution from this fixture, contribution from this fixture, contribution from this fixture, and contribution from this fixture. See how complicated that is? And to add salt to injury, you could also contribution from every single fixture in the area could contribute. And also you will have reflected light to add salt to injury. There will be reflected light from the walls in these areas. You see how complicated the calculation that this software is going through? Reflected light and direct light. To get you the calculation, thanks God we have the software, we don't have to do it, but we will be doing just sample version of it by hand. Can I have thumbs up, Chad, what you're trying to do? So let's go calculate that point by, show you how this formula to calculate it by hand. We don't do it by hand, as I told you. Okay, so let's go back here into, here's the beginning of everything. It's called light intensity. Light intensity, the foot candle, is the candela power in lumens. That's how they define it. The candela power in lumens of this is called the point method. It's in lumens. If you guys look at lighting fixture, remember when you were looking at it, it was saying 3,000 lumens, 5,000 lumens, 6,000 lumens. That's the unit that we measure light with. Not with dollars, not with yens, not with shekels, with lumens. So we take, here's the candela power, that's lumens, divided by the distance squared. Remember that distance from the point into the light? From that light into the point, square that distance, divide the candela power by it, it will give you the foot candle. It will give you the foot candle. Can I have thumbs up, Chad? We fully understand that? That's basically, we're going to do calculation based on this formula. Take this. I have a source of light here. I have a distance. Here's my distance. And I have the area that this source is going to give light to this distance. My friend Jamie's head is the area. The light is right there, and the distance between Jamie's head and the light. That's what we're doing, calculating. So we're going to find how many foot candle goes into Jamie's head. You take the candela power from this. There are 3 lamps. Each one of the 2 lamps are there. Say 2 lamps. 2 lampers multiplied by 3,000 lumens. How do you know the lumens? It comes with the bulb. So 3,000 times 2, 6,000. So you take a 6,000. Let's just say there's 3 lamps here. Here's my 3 lamps. And let's say each one of them is 3,000 lumens by manufacturer, multiplied by 3, divided by 4 by 4. Now, Aaron's head is not 4 by 4. I hope not. So if you want to find an area of 4 by 4, so you take, here's an area of 4 by 4. That's the area. Do the math. It will get you how many foot candles here? 563 foot candles. Did I do the math right? I'm sorry, the area, the distance here. This is the distance from the source of the power. So you take the distance, give you 563 foot candle, right? Did we do the math right? One more time. You take the how many lumens in a lamp, multiplied by how many lamps, divided by the square of the distance, will get you 563 foot candle. We will do calculation, guys, as we move on to the floodlights. We will use this formula a lot. So for the time being, do me a favor. Remember, candela power divided by the square of the distance, the squaring the distance, give you a foot candle. That's how visual does all this calculation. Imagine how many calculation you need from each one of these pictures. Do you guys appreciate what visual is doing because of that? Okay, that's all what I want to get your appreciation on that one. Contrast. We talk about another concept that talk about contrast. In order to see things, guys, in order to make things stand out, you have to make the object shines and the surrounding darker. Does that make sense? Do you see in theaters? What do they do in theater? They have spotlight and they shine it right at Jeff when he's singing, and the surrounding will be what? Dark. That's what they call it contrast. To make things shine, you have to make the object a lot of light on the object and very little light in the surrounding. To make things disappear, you put the same amount of light on the surrounding as well as the object. Can I have a thumbs up for contrast? What contrast is? Who cares about contrast? If you guys being certified lighting designer, you can make things look cool if you play with the contrast. Cool? So that's it. Contrast. So everybody understand the intensity, light intensity calculation. We will do calculation based on this, guys. I will promise you as we move forward. This is just intro. The contrast. The last thing I'm going to talk about is foot candle recommendation. Thanks God to an organization called IESNA, International Illumination Society, and NA. It's an international organization. International Illumination Society, then they add NA, North America, the branch of North America. But they're international. International Illumination Society of North America. Now, I'm sorry? Illumination?
What do they use in
I'm sorry, International Illumination Society of North America. What did they say? Illumination? E. Illumination. I thought illuminated with I. Illumination. Now you're confused, Chad. Now you got me into the spelling. Well, let's go here. I'll show you. IES. It is an IES because the files are IES. What the E that stands for? Go search it. Of North America International Society North America. What the E stands for? What the heck? Illumination? I thought it's illumination. Might lie to you. Let's go to this software right here. Here's my software open. I wanted to show you something here. Okay, so let's go to tools. And under tools, I'm sorry, thank you. Illumination Engineering. E for engineering. Thank you. Illumination Engineering Society of North America. Is it Illumination or International? Illumination Engineering Society of North America. That's it. Illumination Engineering Society of North America. International. Illumination Engineering Society of North America. Cool. We got it. Finally. Okay. So a couple of things, guys, I want to show you in a second here. There's recommendation, IES file recommendation. And if you guys, can you guys look at this page here? They have recommendation for different industries, how many average foot candle you need. Everybody can see that. So for example, examples for suggested mean horizontal foot candle value. What does it mean? What does mean? Average. What does horizontal mean? Horizontal. Because what's the opposite? Vertical. There's vertical and horizontal recommendation. For example, parking lot in industrial plants, they give you 0.5 foot candle. Remember that when we did 0.5 foot candle? Anyway, look at these guys. But what I want to show you is the most updated one from the IES. The most updated one is coming from Visual. So if you come to Visual, you're familiar with that software. If you guys go to Tools, please, and IES recommendation. Can you guys see where you find everything, all these recommendations? Go Tools, IES recommendation. When you go here, it will tell you, do you want to go interior, industrial, outdoor, sport, transportation, emergency? Let's just go interior. Cool. Here's my interior. And since we're office building, so it goes by the location. So I thought there's an office element, no, further down. They're alphabetically, just find it.
Yeah, towards the top, under museum.
Okay, here you go. Office. So they're alphabetically, all the location. Let's go to office. When you go to office, they split it into area. In the office, if you have an area with filing, so see to read, filing. The area in the office where you do filing, can you guys see the horizontal recommendation by the from the illumination or the IES recommendation for it? Everybody can see it. Illumination is 50 average, and it's important. Category E, common, visual test. So give you some description. Since it's the horizontal, what's the vertical in an office on the walls? What do they recommend in the walls? We didn't do that in the office. What do you recommend in the walls in order for the walls to look? Everybody can see on the walls what's recommendation? Right here. 10-foot candle on the walls of a filing area and 50 average on the floor. 2.5 feet. Can I have thumbs up, Chad? That's it. These are the recommendations. The ones that I gave you guys in our specification is coming for the most part from here. Okay, let's go look at another area in the office. Let's look at so open office. Here you go. Open plan office, intensive VDT, use open office, intermittent VDT. So let's use the intensive one. People are sitting there at all times. Can you guys see when you're sitting in an office working, open office, do you see the illumination, suggested illumination? 30-foot candle. You're working computer. You don't want to have a lot of light on you. Important, on the walls, when you work in an open office, what do they recommend? 5-foot candle. Private offices, my office. Let's go to the private offices. These are, in a private office, they recommend 50-foot candle, average, and on the wall, 5-foot candle. Can you guys see all these IES recommendations? Can I have thumbs up? We understand what I gave you for the project is coming directly from this IES file. Cool? That's it. That's what I want to show you. Every location, if you guys can, this is just office. Every location, lobby. I don't know if you guys can see. Here's the lobbies, lounge, and so forth. They recommend 10-foot candle. Not a whole lot. 10-foot candle. People are mail sorting. Mail sorting 50. You need to be able to see when you sort mails, right? So they give you horizontal and vertical. Horizontal and vertical. I need thumbs up that we understand, Chad. Cool? Okay, so that's what I wanted to show you. This is directly from Visual. And in your book, they have a couple of schedules here, very tiny little ones, but in reality, in Visual have tons of the IES. Illumination Engineering Society of North America. Did we get it right? Finally. Illumination Engineering Society of North America. Cool. And all the files that you guys picked yesterday for Visual, they were the extension of the file was what? IES file. They're all IES file. Okay, so we got that one. Got this the illumination. Any comments? Any questions, guys, about that? Any comments? Any questions? So that's basically what chapter 1 is all about. Get you the calculation. As long as I have you and have your divided, semi-undivided attention, I'm going to flip you guys directly into my chapter 2 and excuse the mess here that I gotcha. Okay, let me go. Okay, can you guys flip to chapter 2? So first chapter 1 talks, please read them. One time, please read them. I used to get the IES manual, guys, for the students to buy. It's close to 800 pages. It's just overwhelming, and it's needed only if you want to be a certified lighting designer. This is a nice book, nice introduction for all these systems. Okay, chapter 2 talk about light sources. Light sources. I'm going to summarize chapter 2, guys, for you with a couple of things here. Number 1, light sources. So we know the science light. We know when we generate, we have to generate in the visible spectrum. Then we're going to talk about light. And excuse my mess here. There are 8 light sources that you can generate other than God's light, which is the sun, right? There are 8 artificial industrial light that you can generate for the most part. Cool? Lighting number 1 is incandescent lamps. Number 2, fluorescent. Number 3 is mercury, vapor. Number 4, metal halide. Number 5, high pressure sodium, low pressure sodium, LEDs, and induction. Can I have thumbs up, Chad? These 8 types of lights that you can generate. These are the bulbs, not the fixture, the bulb. Cool? Can I have a thumbs up for the bulb? So let's look at each one of them at a time. Incandescent lamp, that's your grandma's light. They're being phased out in the commercial industrial. You cannot, very specific application for them. You would never use it. That's the incandescent lamps. 80% losses. This incandescent lamps is used, guys. This is used to cook eggs. Literally, you can put 100-watt incandescent lamps, and you can fry an egg on it. 80% losses, the energy that goes into it, 80% losses, only 20% is generated to light. The rest is heat. So if your intention is to heat and lit the place, that's a great application, right? Definitely here, when we put a light here, our intention is not to heat the place, it's to put light. So drop that one from your commercial. So heaters, well, the way they do, guys, they're inefficient, they're heaters. They have a resistor. They drop the current through the resistor, it glows. That's what they, very simple, straightforward. Tungsten halogen, the way they do, then they treat inside the bulb, that's they use in cars. Inside the bulb, they put the halogen gases in it, and they treat it to make it more efficient by putting gas inside the bulb. Can I have thumbs up, Chad? So it's a resistor right here. They add gases here to treat it, to make it more efficient. Either one of them, I put an X here. What does this X mean? Do not use it. Unless it's specified. In our project, guys, we specified one of them for contrast, because we want to throw light on the wall, just to make sure the Mona Lisa is showing up on the wall. Okay, so that's the first and the most fundamental lighting fixture. Drop it. Can I have thumbs up, Chad? Okay, let's go to fluorescent mercury metal halide and high pressure sodium. You can see that green, the blue stuff. These are called the arc lamps. There are two ways of generating light. One way is to heat a resistor and glows. That's the incandescent. The other way is by creating an arc. Fluorescent here, the way they do it, guys, they bring the voltage across the anode and the cathode. They pump the voltage so high inside the bulb. The voltage is so high that created an arc. What happened if the voltage, you guys, do you remember Jacob's ladder? Did you see Jacob's ladder with Gary? You guys seen Jacob's ladder. What happened if you put high voltage and you put the conductors, uninsulated conductors, right to each other? What happened? Jumps. That's the arc. That's exactly what they do here. On the anode and the cathode, they raise the voltage so high, much higher than 120, that it creates an arc. The arc shoots from one side to the other side. Now we're having an arc. Now you create an arc in this bulb. Cool. Now to maintain the arc, they have a ballast. The ballast itself first pump the voltage so high to create the arc. Now we have an arc. Now we need to maintain it. Otherwise, if you don't maintain it, this circuit breaker will trip, thinking you have an arc flash and circuit breaker. Arc flash and circuit breaker will trip. Then the ballast will reduce the current to an acceptable level, guys, and by maintaining the arc. So the ballast pump the voltage up, start the arc, and then choke the current, reduce the current down to acceptable level, so the circuit breaker doesn't think it's an arc flash, short circuit, and trip. Then create an arc in that bulb. Now this arc is ultraviolet. You can't see the arc. So the smarter than Chad, Ian, my friend, is what they do is they treat the inside of the bulb with some phosphorus material, and that material, chemical material, it will convert the ultraviolet in visible light. And that's what you're looking at right here. Can I have thumbs up, Chad? That's why they call these arc. So fluorescent light is an arc. Mercury, metal halide, and high pressure sodium, all these are an arc, and they need a ballast. Incandescent lamp don't need a ballast. Okay? So let's look at the fluorescent light. The first arc light, you can use T5, TA to T5. The 5 guys stand for the diameter, so to indicate the diameter. So if you take the 5 divided by 8, that will give you the diameter of this fixture. So when you say T8, 8 divided by 5, give you the diameter of that fixture. I'm sorry, T8, 8 times 8. We always divide by 8, that magic number 8. So when you have a T8, the diameter of that fixture, 8 divided by 8 is what? It's an inch diameter. T5, smaller. How about T12? Fatter, okay? Which one is the best? T5. The smaller the diameter, the more concentration of light you get, the better fixture you have. Can I have thumbs up, Chad? In your project, guys, we are using T8 and T5s, if you remember. T5s are more, they give you more light, concentration of the source of the light. Okay. Where would we use incandescent? Typically inside, indoor. Your project, guys, is all incandescent lamps. Fluorescent lamps. Cool. Any question, guys, about the fluorescent? The best application for fluorescent is office buildings, Interior. You can use them outside, but office buildings, interior. Can I have thumbs up, Chad, for this type of source? Let's move into the other one. So we have low intensity discharge. The fluorescent is called an arc fixture with low intensity discharge. The discharge current is low. Then the other three guys, 1, 2, 3, it's also arc lamps, but they have high intensity discharge. The arc is bigger arc. So the smarter than Chad said, what if we want a bigger arc? Then they created that metal halide. Metal halide, the same thing, the same principle. Mercury vapor gas, same principle. You start an arc, you maintain the arc, you treat the arc with mercury. What's wrong with mercury? Environment. So if you're a tree hugger like my wife, and the frogs are, instead of having 4 legs, now they have 1 leg or 3 legs. They're missing 1 leg because of mercury, and rightfully so. Believe me, I believe in it too. So then we don't want mercury. So what did we do to the mercury? We phase it out. We don't use it because of environmental reasons. The mercury, cool. But the way they do them, guys, they start the arc and they put mercury there, and the mercury will treat the arc into visible light, make it much better, big floodlight visible light. Okay. So you can use it outdoor or indoor. For outdoor, like in a bigger space or indoor. Then we move into another arc, metal halide high pressure sodium. Right now, so everybody knows why I crossed the mercury here, because of environmental reasons. Fluorescent light is your fixture of choice after LED now, if you're doing a commercial building. Your fixture of choice is a fluorescent light, like you guys have done with me, right? So that's why I get the check here on that. Then moving into, what if you're doing parking lot or manufacturing floor? You have 2 options, metal halide or high pressure sodium. Both of these, the only difference is the chemicals that they use inside them, guys, to get you the light. They treat the light. So be aware, if you're doing a parking lot, did you guys remember MH fixture, that CAD fixture that we used? Do you guys remember that? That was coming from metal halide. We used metal halide. Typically, metal halides are commonly used in parking lot. High pressure sodium, also you can use them in parking lot, but streets and highways and so forth. There's also low pressure sodium. Low pressure sodium, their problem, anybody knows what the problem of low pressure sodium? That's the chemical that they use with them. They have color discrimination 0. Oh, we didn't talk about color discrimination. When it comes to light, color discrimination is the best thing that you can find. You need to be able to see green, not blue, right? That's what the color rendering index. They have a color rendering index. Fixtures are labeled based on how good of a color rendering index they have. So if you come up to a low pressure sodium, good luck finding your car in the parking lot at night, because you're not going to be able to see it. You will see everything almost gray, right? Black and white and gray. Okay, so can you guys highlight high pressure sodium, metal halide are your light of choice. Your light of choice if you're doing parking lot and open space and open areas. Can I have thumbs up, Chad? Because of 2 things. Number 1, they give you a lot of light. And number 2, they have a good color rendering index. Okay, so that's why HID, high intensity discharge, they call them. These are LID. The fluorescent is LID, is low intensity discharge. So the way all these arc guys, they have a ballast, they generate ultraviolet, they treat it, then it gets into visible light. Everybody understand when we have an arc fixture, you need a ballast to pump the voltage to stop the arc. When you stop the arc, you create an ultraviolet light. Unless you are not human like us, you can't see the ultraviolet light. So what do you need to do? You need to treat it with some chemicals. Mercury is one of them. Sodium is another. Treat that boy into visible light so you can see. Can you have thumbs up, Chad, with that one? Okay, so these are your lighting sources. The last 2 are becoming big deal now, is LEDs. LEDs are really cool. The reason for LEDs are cool, guys, because they are efficient. They don't generate a lot of heat. So what they do with LEDs work on a different principle. Is you take AC, convert it to DC, and put it into a diode, and the diode will illuminate. Tiny little diodes will illuminate. That's a principle of work for LEDs. No ballast, nothing. But what do they need instead of a ballast? What does an LED fixture need? They need a driver. What's the driver? The driver is almost a ballast, except you have to take the AC, convert it to what? DC, dump it into these little diodes, and these little diodes, they are MP junctions, and you put pressure across them, 24-volt pressure across them, and they illuminate. okay, with good efficiency. LEDs right now, indoor and outdoor, they're becoming unreal. Next project, my friends, you will mark your words. Next project, there will be 100% LEDs, indoor, outdoor with Chad. All of them are going to be LEDs. Why? Efficient. They're still expensive. Their idea is still expensive. Induction heat. I don't know how many. If you guys search induction heat, it's not commonly used, but they use the principle of induction like motors. They induce induction, not induction heat. They induce light through induction, magnetically induced light. Not commonly used, but my understanding is a good application for it in hazardous location and places where you don't want to have current moving around. You can have induction light through induction, like a motor. You induce a magnetic field into a bulb and you create light. You can search online. Not commonly used, but that's another application. So I want you guys summarize of everything that I've done here. Incandescent lamp, open the window, throw in the garbage. Fluorescent lamp, your conduit, your fixture of choice if you're doing indoor lighting calculation, office and so forth, your fixture of choice, T5TA. Mercury, it kills a lot of animals, we don't want it. Metal halide, high pressure sodium, your choice of fixture when you're doing outdoor and parking lot. Thumbs up, Chad. Then low pressure sodium, they use them sometimes in the highways, because in the highways, if you're driving at 85 miles an hour, do you really care what color, unless you're police, what color light, vehicle is next to you? You need to know that you can see it, right? But do you really care if it's blue or red, unless you're a policeman and you want to report it? So that they use them, or they used to be a lot used in the park. They're very efficient. They give you light to see, but not to distinguish between colors. But who cares when you're driving at 85 miles an hour? Okay, so you can't, obviously in a parking lot you can't do that because we don't do street highways. So metal halide, high pressure sodium, your choices. Alternative for metal halide, high pressure sodium, and fluorescent is going to be what? LEDs, indoor, outdoor. Thumbs up, Chad. We understand that one? That's it. That's the sources of power. That's what the chapter is talking about. I can't emphasize, this will be PDF, guys. I know it's a lot of information in it. But really, that's a source. That's all the sources put together. They're commercially available sources. Between fluorescent and metal halide, that's our project is made of two things: metal halide and fluorescent. And next project is going to be made completely out of what? LEDs, indoor, outdoor. Cool. So that's basically the sources. And just to summarize, guys, there are two types of lights, major types. One is non-arcing, that's the incandescent light, no arc. The other one is arcing, fluorescent and high intensity discharge, right? The arcing has two types. One, low intensity discharge, fluorescent. The other one is high intensity discharge. These are the mercury and metal halide and high pressure sodium. And then the third part is the LEDs, major part. Any comments, any questions, guys, about this? Any comments, any questions? I'm not going to go over chapter 3. I'm going to stop right here. Any comments, any questions for this particular? This is the light source. If you guys look at in your book, it tells you the lighting fixtures make out of a bulb and a base. And I'm not going to go. There's so many types of bases, guys, that you can look at. If you look at page 12, incandescent lamp base types and incandescent lamp shapes. There's different shapes of incandescent lamps. Same thing for fluorescent lamps, high intensity discharge. I want to take you guys to one curve. I would like you to go to page 19, please. If you go to page 19, minutes of warm-up time and percentage of normal. If you guys look at lamp, this is a warm-up characteristic for mercury vapor. It shows the disadvantage of high intensity discharge. Anybody knows what the disadvantage of high intensity discharge? They need time to warm up. They need at least 5 minutes to come up to full speed. And when you turn them off and turn them on again, they need 15 minutes to come up. So that's the. Go ahead.
They have to cool, yeah.
Yeah, they have to cool down to acceptable level of income. That's a drawback of mercury, metal halide, and high pressure sodium. Because the first they need 5 minutes to come up to speed, meaning go to full brightness, right? And then when you turn them off and on again, they will take 15 minutes to cool down and come up to speed. Now, can I use them as an emergency light then? No. You lose the power, you try to ignite them again, they can't use it. So that's a drawback. That's why fluorescent is taking over. High bay fluorescent, we're going to talk about this one, guys, in LEDs. So minutes of warm up. This curve, it shows you the minutes of warm up, guys, for the light output, lamp voltage, and lamp amps. I don't know if you guys can see as the voltage starts going up, lamp voltage. Look at the voltage going up, 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 up. As it reaches 100%, like 277 voltage, the light output is also going up, and the current is going down. Can you guys see? You have an inrush on it. When you start, you have 160% of the full load current, inrush. And then it goes down all the way after 5 minutes or so. In this case, it's 3 minutes. After 3 minutes, the fixture will come up to a full speed. So, long story short, when you have a fixture, a high intensity discharge fixture, you have to be aware that when you turn it on, it will take a couple of minutes to warm up. The voltage ramps up, the output will ramp up, and the current starts high and goes all the way down to full load current. That's what this curve is telling you. Any question, guys, about this curve? The arc flash, the arc is coming. The reason why the current is high because you have an arc. An arc is almost a short circuit. So for a while, the arc goes so high that now you need to maintain it. What happened? When the arc goes so high, the ballast start reducing the voltage, and the current will start going back to its normal level. Yes, you start with an arc. That's why the current is high and the voltage low. If you guys look at page 19 at the bottom, lumen and life characteristic of mercury vapor. After 24,000 hours, your mercury percentage of lamp still burning, the percentage of lamp that's still burning for this is for mercury, it's 24. So 60% of the fixtures will be burning after 24,000 hours. This is how good of a fixture is. If you look at lumen maintenance curve, after 24,000 hours, percentage of initial lumen, mercury after 25,000 hours, 40% of the lumens coming out of this one is left. What happened to the other 60%? Down the drain. You can see these curves. Every fixture has a curve. Can I guys emphasize one thing? After you put the fixture, do you expect the lumen, the same amount of lumen to do it? There's chemicals in it. The longer it takes, two things are going to happen. The lumen is going to go down, and the fixture is going to die on you. So how long will it take to die for the fixture, and how much of the lumen you're going to lose will decide how good of a fixture you have. Okay? So that's when you start specifying fixture. It's a big deal. If you guys go to page 20. If you go to page 20, they have lumen and life characteristics of high intensity discharge. They're comparing a bunch of them. They have first they have metal halide and high pressure sodium. I want you guys to look at this curve and tell me that you can see that metal halide, high pressure sodium is superior, because after 24,000 hours, I have the percentage, it will maintain 80% of their lumen. Can you guys see that? After 24,000 hours, it will maintain 80% of its lumens. If you guys go to mercury, the mercury after 24,000 hours, it will maintain only 40% of its lumens. So which one is the best? Metal halide and high pressure sodium. So high pressure sodium maintains 60%. So anyway, all these curves, guys, to convince you that high pressure sodium is better than metal halide and metal halide is better than mercury. Okay, so that's that one. In page 21, I'm going to look at the curve too. Page 21, they have warm-up characteristic for high pressure sodium. It takes almost 6 minutes for high pressure sodium to come up to speed. Can you guys see that? The light output, the lumens start, can you guys see the lower curve? The lumens start going up, 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 up to its full value. The current start going down, down, down to its value. Can you guys see that? The current, the lumens going up, up, up as the current start very high and start going down, down to its acceptable value. That's the inrush. as you flip the switch, the current is going to go high, inrush on the fixture for 5 seconds. Then the current starts going down, 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 as the output, the lumens, start going up, 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 up to reach the 100% value. Okay, for both of them. Anyway, so if you guys want to sit for your certified lighting designer, these are big deal. The last thing I want to show you is that graph at the end. If you guys look at this graph, efficiency comparison of different types of lamps. Can you guys see efficiency in lumens per watt? Efficiency of motors are measured in lumens per watt. How many lumens per watt you can generate? Look at the incandescent lamps. The top one, 20 lumens per watt. See how disgusting that is? Compared to the mercury 55, to the fluorescent 100, metal halide 125, high pressure sodium 140, low pressure sodium is 200. Perfect energy conversion is obviously is 100%. So can you guys see the superior in terms of efficiency is which fixture? Which fixture? Low pressure sodium. What's the problem with low pressure sodium though? We talked about it.
Takes forever to warm up.
All of them do, but they have a specific problem with low pressure sodium. Color discrimination is almost zero. You can't distinguish between colors. So can you guys see why high pressure sodium, metal halide, and fluorescent are the lighting of choice? Now LEDs are also it's not here. LEDs will exceed all of them. Can I have thumbs up how we read these? Okay, so that's what I want you guys to do on that one. And the last thing I want to show, I showed you guys these. I want to show you one thing to find if you go to Lithonia, if you guys go to, this is Lithonia site. If you go there and you go, this is Acuity Brands. If you go to Acuity Brands, I have it, guys. This site is in student, the collection of sites that I gave you guys in the instructor folder. So you go there. You can click in Gotham if you have light in Gotham, but we also, or you can use Lithonia. Oops. So it gives you any type, and let's use Lithonia. This goes hand in hand with the book that you have, guys. Hand in hand. So let's go to Lithonia first. Click on Lithonia, and if you click here, it will take you to Lithonia fixture. All the fixtures in Lithonia. Everybody can see that? So we went to, now we're moving to Lithonia. If you go there, I need to have commercial industrial fluorescent. Can you guys see that? Click on commercial industrial fluorescent. Cool. Commercial industrial fluorescent. Let me see, where did they go? Commercial industrial fluorescent. Does resist sound familiar to you? I actually want to use parking outdoor. I'm going to go outdoor. Do you mind? I'm going to go outdoor because I want to show you something. Outdoor. Outdoor. And for outdoor, I want to use parking lot, poles, parking lot and garages. Parking lot and garages. I think the one that I was looking for that I found is area light. Area light. Click on area light. I don't know why it's going twice. Area light. Okay. For area light, I think it did it. There you go. For area light, I have different series here. I think I did CAD right in here. Here's the CAD fixture. When you click as an area light, you're going to find a CAD. I went directly into the CAD fixture. Here's a CAD fixture that you can do that one that we did. If you click on CAD fixture, that's the one that you guys did in the parking lot. If you go to specification, click on specification, it will give you the spec for this fixture. Here's a specification. That's what you guys are going to give me. You're going to give me a specification. Come on, come on, come on. There you go. It's cooking. Okay, this is the CAD fixture. What I would like you guys to look at the description of the CAD fixture. It's a CAD. Now, can you guys see metal halide? Does that sound familiar to you now when you look at metal halide? This is a metal halide fixture, right? You can have metal halide, 70, 100, all the way to 200 is the watts, all the way to 400. Can I get these suckers as high pressure sodium? Can you guys see that next to it, high pressure sodium, right? And there's a second type, there's three types. Yes, ceramic, metal halide, and metal halide. Don't ask me the difference, but there are three types. Two of them are metal halide, high pressure sodium. Then, distribution. Do you guys remember how R, R2, R3, R4, and we used R3? This is it going to project all the light forward or horizontal or somewhere in between? 3 will project it this way, 2 will project it this way, and 4 will project completely this way, right? So it depends on your application. So here's all your stuff. Voltages. Can you guys see all the voltages I can burn these suckers at? And then ballast. You have magnetic ballast with these almost always, or pulse start. The efficiency, you need a pulse start on them. And then mounting, single pole, round pole, the mounting that you will mount them. Arm, how the length of the arm, 4 inches or so forth. Options, you have single fuse, you can have fuse, double fuse to fuse the circuits coming to them, and so forth. So this is what I would like you guys to see when you look at that. Now right underneath it, can you guys see the ISO illumination curve for these fixtures? If your fixture is sitting right here, this is how it's going to distribute the light around it. This will be the topic for tomorrow when we do ISO. These curves are the lumens per foot candle on the parking lot. And can you guys see 1, 2, 3, the distance and the distribution of the light in this parking lot? Again, thanks God, lumen. Thanks God, guys, the visual has all these curves. Remember how you would drop it and it drops with that curve? That's what they're talking about. You drop that curve, overlap them, done. But this is coming for each one of these fixtures. Here's a really nice stuff. Mounting height. Mounting height, guys, if you have existing mounting height divided by new mounting height multiplied by 2, give you a correcting factor. We don't get into the correcting factor. This is obviously the higher the fixture mounted, the more it's going to throw the light. You lower it, it's going to throw less. So there's a distances that comes with it. We'll talk about this one, guys, as we move forward. But these are the ones I would like you guys to look at. Any comments, any questions, any comments about these? Yes, sir.
Are we supposed to be doing that at 0 feet for where we're measuring?
No. This all the calculation that you get it at a certain height. 10 foot is typical, and then from 10 all the way to 30 feet. So you have the fixture, say 12 feet right now, and right where Jamie's sitting right there, and you do the calculation between the working space to where it's going to hit. You're going to see how we do calculation outdoor and inside slightly different. So it's coming. The whole calculation is coming, believe me. Okay, so that's basically, I just want to show you guys a brand new fixtures that you can find. By the way, I want you guys to write the catalog number for this fixture for me. When you give it to me at the end, these are cut sheets. That's how you cut sheet this. I think it allows you to type. Can you guys see it allows you to type here? So catalog number, you put your catalog number right here. Then you put notes. Chad is good. And then the type of the fixture is type D. Okay? So this, and then you print it. You PDF it. That's how typically engineers work with these cut sheets. You give them to the electricians. Now you know exactly what type of fixtures, what any notes, if any, and what's the D. Everybody knows what D is. D, how it's going to show on the plans. So when you see fixture D, that's going to be actually a CAD fixture. Can I have thumbs up, Chad? We understand the cut sheet? Okay, cool. The last thing I want to show you guys is when you go to the, and by the way, I picked the CAD. You can go and find it for any fixture that we use. Now, do you guys remember something called Revit? Anybody remember Revit? Do we deal with Revit here? So, another class. If you guys see the specification, that will cut sheet. If you go to building information modeling, click on that. Can you guys see where it says it gives you the family? Click on the family. Click right here and open, and off it goes downloading the family for this fixture. Okay? All right, here you go. Can you guys see that? Does that look familiar to you? There are two things. They give you a CAD drawing of it as well as a Revit. I need everybody to give me a thumbs up. So next week, when I ask you gentlemen to go grab your fixtures, I already have them in one location for you guys, but I encourage you strongly to go find the CAD fixture in the catalog, find the Revit, then you can save it. Right now, it's in a folder right here. I can copy it and go take it to my folder on the network and dump it right into a folder that says families, lighting fixture families, and then load it into where? Load it into Revit and drop it right where it should be. These are the ones that I gave you guys are old ones. Then brand new ones, the exact, if you work in the field right now, that's exactly what I have done, is exactly what you do. These are directly from the manufacturer. Cool? So that's what I wanted to show you about the Revit families, any one of them. So that's basically additional images. You can get additional images for that. You can get the poles that goes with it, for indoor lights, emergency light, downlight. So anyway, so that's, go back to Lithonia. Instruction, installation instruction, building, photometric data. Here's the photometric data cutoff. Let's click on that one. Here's the photometric data for this fixture. Can you guys see that? Who cares about these? These are the IES files that we have from the fixtures. You can find IES files. You can grab an IES file and download. Here's, can you guys see the IES files here for that fixture? You can grab this. We already have them in our project. But in the field, when you go start working and you find a fixture and you don't know where the IES file of it, you can load it. Where are you going to go? To the catalog number. Almost all the manufacturers, this is Lithonia, guys. Almost all the respected manufacturers will have a cut sheet for the fixture, an IES file about the fixture, a CAD, and a Revit. 4 things. A specification sheet about the fixture, a CAD, a Revit, as well as an IES file about every fixture that they offer. If they don't do that, they are not respected manufacturer. You shouldn't buy their product. Is that judgmental? Most time. Okay, so that's what I want to show you guys. So that's about it. Any comments, any questions? That will cover chapter 1 and 2. Tomorrow, guys, I'm going to go over 3 and 4 and do some calculations. So as I do the calculation by hand, I'm going to be referring you to this site. Can I have thumbs up? We're good? Okay. We're going to wait for our speaker in a second. He should be here. So why don't you guys have a break? Thank you.